to put some jabs into ESCOM and stuff. So I'm going to talk about, it's a light stupid. It's a simple stupid I didn't know what else to make the topic, so I just thought I'll put that out. So it's quite experimental stuff, so it's pretty much work in progress. So this is not an end product at all. So I'm just going to take you through some of the things that we're working on at the moment. You may find it interesting, you may not find it interesting. We'll try to keep it interactive, so if you got a comment, you're welcome to talk. So the first question is, do we trust our government? And I would assume the majority of you would say no. We don't trust government at all. And our belief is well-founded. There's a number of studies that have come out these days or the past couple of years that have tried to gauge the trust levels of nations or peoples in their governments. I'm just going to put a couple of. In the EU, only 43% trust their government. In America, 18%, 10% of Australians, etc., etc. There's a couple of others. Interesting if you look at the bottom. One that says more than 70% of the people that surveyed in South Africa rather trust the private sector than they trust government, which I found quite interesting. I wouldn't think that would be a significant number, but it seems like it's indeed the case and stuff. So that's the first question that I want to, and that leads into the thing about if we say we don't trust government in general, then why should we trust the numbers that come out of government? Because government is in general the official statistical supplier of all economic data. So the question, if you don't trust your government in general, then per definition you shouldn't then trust the statistics that come out of the various statistical offices. I do actually believe that we have a very good statistical office in Stats SA. I don't think there's too many issues. But in general, the question is, if we don't trust our governments, should we then trust the statistics? And so there's a couple of papers that came out recently on the issue of GDP fraud, where people say, okay, there's a lot of fraudulent statistics that are being thrown around, specifically around the issue of China. A lot of work has been done to try to estimate the real GDP of China, not the published numbers of what comes out of China. Some statistics go as far as say they overestimate by 3 to 4% their official data statistics and all of these sort of things. So there's a couple of papers and a couple of comments in terms of exactly this phenomenon. And they found that in many, many countries, at some point, some of the official statistics were manipulated for a specific political purpose, and obviously it goes with the election cycle. The closer you get to election cycles, the more optimistic the numbers go, and so forth, and so forth. In South Africa, we've got the case like the government will throw out the strict definition unemployment numbers, and the opposition party will throw out the expanded definition of unemployment. So the government will say, oh, our employment is only 29%, and the opposition will say, no, it's actually 40%. So both are right. It just matters, which definition of the unemployment rate you use, et cetera, et cetera. So it's a long story, but what I want to get to, well, just give you some numbers. This is, I won't tell you which country, you can guess later, but those are the GDP numbers of a specific country from October 2016 to April 2019. Now, if you ever have looked at quarterly GDP numbers, you would look at that numbers and say something is wrong. Because quarterly GDP doesn't go that smooth. It's normally quite up and down and stuff. So that's China. That's the Chinese official GDP numbers, quarterly GDP. And I mean, you've got 6.8, 6.8, 6.8 for 3 consecutive quarters. That doesn't seem plausible at all. And then if you look at the stepwise coming down, it's 0.1% every quarter. So it looks quite manufactured. It's not supposed to look like that. Okay, so that just gives you an intuitive feeling of what potentially can happen with these numbers. That's quite interesting as well. I won't say which country that is initially. That is a GDP per capita. Now, does that number make sense? Also doesn't make sense. Flat, 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 and all of a sudden, it just went from, 96,000 to 629,000. That's Venezuela. That number is from Venezuela. Now you need to understand this in dollars. So you need to understand that it's not because GDP per capita went up, it's because their currency just plummeted. Exactly. So it's easy to manipulate. If you're Venezuelan, you think, here we are rich. Shit, we are a rich country. Okay, meantime, it's a very manufactured number and stuff. If you look at this number, so that was China and Venezuela. If you look at this number, that is changes in stock. You know, that's normally your residual in your GDP number, you know, that you cannot sort of account for. You can also see nothing, 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 and then just go crazy. And that's Norway. That's Norway. So I just showed you sort of 3 examples where you can just look at the statistics and say, ooh, that something smells. Not the salt pans here, but there something doesn't look 100% correct. So that's the premises. The first premise is that we don't trust our government, and therefore we shouldn't just take the statistics at face value. And I just showed you some numbers that looks fishy. So the two seems to collaborate one another. So this brings us to that little slide, and this is really where the presentation sort of starts, is where people are looking at alternatives, and they're trying to find other ways to collaborate the official statistics that are published. And this is where the issue of satellite technology comes into play. So my talk is really going to be about satellite technology as a way of looking at numbers like GDP, for example. So that's really what the whole thing was. So if you look on the left-hand side of the graph, you see that the red one is the official GDP statistics, and the blue is the derived statistics using satellite technology. Okay, so what they say is in the more developed countries, there seems to be a very one-to-one relationship between what the statistical offices publishes and what they have calculated their GDP to be based on satellite technologies. Whereas on the right, you see quite a big difference between what those countries' published GDPs are and what is derived from satellite technology. So the assumption is that you can use satellites and the satellite remote sensor imagery to try to develop alternative statistics. And those statistics you can compare then with the official statistics to see whether there's a disjuncture between the two, whether there's in fact GDP fraud or not.
Sorry, the biggest discrepancy is between 3 countries.
No, on the right-hand side is not free. Not free countries. So this is the light growth, okay, and that's the GDP growth. So, sorry, do I have it right? So this is GDP growth, and this is, yes, you're right. Do I? Yes. Yes, it should looks like it should be the other way around, am I right?
I think there's something wrong with that chart.
Yes. I'll phone Martinez and ask him. Okay, so those are well-known pictures that most of you have seen, am I right? On your right-hand, my left, your right-hand side, my left-hand side is South Korea, North Korea. In fact, that's where the technology originally occurred, is that the US military was looking at the issue of North Korea. North Korea has got no official statistics. So they tried to estimate the GDP and those sort of things of North Korea. And this is where the whole thing sort of developed and stuff. And so the right is just also lights, but okay, I'll explain a little bit about it later. Okay, so those are the satellites. Those satellites were sent up in the late 1980s. Okay, there's 2 sets of periods that we're going to play around with. Okay, the first set of period is 1992 to 2013. That was what they call the first generation satellites. Then those satellites became obsolete, and they sent in 2012 new satellites. So we can actually sit with 2 periods. Okay, the old satellites from 1992 to 2013, and then the 2012 satellites to the current period. Okay, so on my left-hand side, DMS-P F10, those are the old satellites. I'll show you the orbits and the times and all of those sort of things. And the NPP satellites are the new generation satellites that's currently floating and hovering around us at the moment. So those are really where the data comes from. Okay, so the old they basically fly the same pattern around the world and stuff, so there's nothing really different in terms of their orbiting around the Earth between the old satellites and the new satellites. The big difference between is the time at which they take the pictures. So the old satellites took pictures around about 4 o'clock to 8 o'clock in the evening, and the newer version of the satellites take between 10 o'clock and 2 o'clock in the next morning the pictures. Okay, so they fly, and so at any time there's about 8 of them flying in a specific orbit. So at any time between that period of time, there's at least 2 to 3 satellites right up above the specific period. And what these satellites do is they take pictures, what they call arc-second pictures. So they take a picture of roughly 1 square kilometer area of the whole world in that specific period of time. Okay, and I'll show you how those sort of pictures look like. But it's important to remember that there's 2 sets of data, which is not necessarily comparable to one another.
Can we just go back to the previous image and appreciate the brilliance of the total operational environmental satellites? Da is die push.
Yeah. Yeah. Excellent. We'll edit that on YouTube, okay? Yeah, we'll edit those on the YouTube. Okay, so that's just again talking about the 2 sets of data satellites. I'll show you the websites where you can get the data a little bit later and stuff as well. But I said the first generation was from 1992 to 2013, but they were pulled out and were replaced by the new generation. I can't pronounce all those long names and abbreviations and all of those sort of things. But important to remember there's 2 generations of satellites. The first generation is worked pretty much on photography, where the second generation pretty much work on what do you call laser type of activities and stuff. So, as I said, they fly around. I'll show you the statistics on those sort of things. That just shows you the difference in terms of the imagery between the old technology and the new technology. So on your right-hand side, you have the picture of using the old technology, and on the left-hand side, you have the picture using the new technology. You'll see on the old technology, there's a lot of blur, so to speak, the radiance of the light. Where the new technology really looks at the true light, not necessarily the radiance included, because the light that shines also has radiance and stuff. What you need to remember is these satellites are highly calibrated, so they are programmed to take out the effects of clouds. They take the effects of all natural lights like fires, glare, gas burns, lightning, and all of these sort of things. So these pictures go through a tremendous process of cleaning up to get to what they call the man-made light. So they try as far as possible to take all these artificial lights and all of these things out. So eventually what you get with this data is man-made light. Okay, and stuff. So that's just the difference between that's why I say it's difficult to perfectly compare the first generation pictures with the second generation pictures. You can't necessarily compare that. Although fortunately there was a period of where these things run concurrently, 2012 and 2013. They run concurrently, so you potentially can calibrate the 2 series to form one continuous series. But you can't change the maps, unfortunately, the pictures and stuff. Okay, so that's how the pictures look like. I'm not going to go through that. So what these guys do is they take, specifically in the 1992 period to 2013 period, they publish the data on an annual basis. So we'll take all the daily pictures, and they will merge it into one annual picture. Okay. But the latest ones allows you to download the data almost immediately on a day-to-day basis. So the data is now on a daily basis available. So you don't have to wait annually. And that's why it's quite attractive to the data, because it's real time, immediately available. You don't have to wait 6 months, 7 months like GDP numbers to wait to find. You can actually download it as they publish the data immediately. Now they publish the data, about 6 different versions of the data. Okay, so they don't publish just one set for every day or every month or every year. There's about 6 sets of data. Some includes natural lights, some exclude it. Some includes clouds, some excludes it. So you really need to understand which of the series are you working with. And I'll show you some of the differences.
Can I ask a technical question?
Yes.
There's a move, especially in rich countries, to install lights that only shine downwards.
Downwards, yeah.
So I would imagine that the radiance from Europe, for example, would actually go down slightly.
Yeah. That's the beauty of the new generation, can pick that up. Yeah.
So it accounts for.
Yes. So obviously these satellites can't look into your house. Okay. They can't look into the factory. Okay. So you need to understand there's limitations to this because they can't look into your house. They can't look actually into the factory. But I'll show you the actual lights and how it works and how it performs and stuff. Oh, yeah, exactly. I'll show you the websites where you can go, can find the data, play around with it. Look, it's huge files and stuff. So it's very consistent data. Okay, so the bottom one is just to show you these arc seconds, how many there are. There are 22 billion arc seconds that they take pictures of. So you're not looking at small numbers here. It's big data. And of that 22 billion satellite pixels, 6.4 billion sits on the land. Obviously, the rest are dark and stuff. Okay, so that's basically, so I'll show you some of the actual pictures look like. But they're all roughly 1 square kilometer, and they are very consistent in that specific location. There's some slight movements in that arc second from satellite to satellite, but they are amazingly consistent. So if this is a arc second or 1 square kilometer picture for this month, it will roughly be the same for next month, roughly be the same for the month thereafter, year thereafter. So slight movements a little bit left and right, but they almost, because they fly in the same orbit and take the picture at the same time, it's amazingly consistent on, they take the picture there. They don't take it here and then there and so forth. So you have a set of data that you can look at over a long period of time, as I said, from 1992. Etc., etc. The other big difference between the two satellites, or the two periods, is that the older generation had a ceiling on what they call the brightness of the light, or the light intensity. It went from a range from 0 to 63. Okay, so it stops at 63. So anything brighter than 63 is capped at 63, where the latest technology doesn't have a ceiling. It can go up from 0 to 1,000. But how do you call it? The pixels are much lower in intensity. So the others were 1, 2, roughly to 63. The others come with decimal numbers and these sort of things. I'll show you some of those as we go along. Okay, so there's a lot of studies that have been done. Most of them have been done from sort of 2008. But most of the studies have been quite recent, in 2013, 2014, 2015 is when most of these studies have been published. So that's just pictures of, if you look at this particular one in Madagascar, where you had a little town there and there was nothing there. And then they discovered sapphire in this little town, and it shows you how this town sort of became smaller, and this little town where they found the sapphire just got bigger and bigger and bigger and bigger. So it shows you clearly from that picture how people moved from this town to that town because of the discovery of sapphire, etc. So they use it in a various numbers of ways. A lot of studies have been done to show the relationship between GDP and these lights and stuff. That's one particular study that looks at that correlation and stuff, and it found to be a very, very high correlation between the intensity of the light and GDP. I'm not going to go for all the studies. There's a couple of them that have been done. So I'm just going to go to an example. So who from you are from KZN? Okay, you know where Lady Smith is? Not the Cape one, the KZN one. Okay. Yeah, so you've got Lady Smith there in the Midlands of KZN. And in the late 1970s, beginning 1980s, the government of that day built a massive industrial estate close to a big informal settlement and stuff. It's called Ezakheni Industrial Estate. You'll see that's roughly the Google Earth picture of it. It's a massive, massive estate. And it really, on the peak of it, it was fully occupied here in the late 80s, beginning 1990s. And obviously then with the deindustrialization, it started moving down and stuff. So at the moment, so that's Ezakheni. I'll just show you some pictures of it. Let me first go to there. This is some pictures of the estate itself. At the moment of that huge estate, there's only 5 industries left. Okay, most of the place is standing empty. Okay, so there's a small little textile factory still left. There's a tent manufacturer. DeFi has got a warehouse there. Coke has got a distribution center there. And that's basically that. Okay, so 90% of that place are standing empty. And you've got roughly about 150,000 people just staying next to it. So that was the intended purpose. You've got this massive amount of people there, you build your industrial state there, and so forth. But as I said, it's basically standing empty. Okay, so that's just a nighttime picture of, just to put you in perspective, a nighttime picture. So you've got Lady Smith on your top left. You've got the estate there, basically lying there. And you've got these 2 massive informal settlements right next to it. Just, as I said, the size of these 2 informal settlements is roughly about 160,000 people staying there and stuff. Okay, so I tracked it through the satellite technology. Okay, so on your left-hand side is the estate. So that is the estate there. That is the informal settlement next to it. So that's the estate. The pictures, that 1 square kilometer pictures that were taken of the estate during the night, okay, in pixel format. Okay, so that was in 2013, and then I put the nightlight picture of that specific estate in 2019, which is on your right-hand side. Now you can see a difference both in the size of the light that it projects into space, and you can also see a change in the intensity of the light that it projects into space. So in both cases, the size of the lights, what we call the sum of lights, have got smaller over time, and also the intensity of the lights, which is the more darker that arc seconds, the more intense the lights are, have also diminished. So I just put it up on the table on your top right, and again I break everything down to those 2 periods of satellites. So you'll see the average light intensity in 1992 was 28, okay, versus in 2013 the average light intensity was 25. The count, meaning how many lit pixels there are or how many lit square kilometers there are, were 28. That's in 2013, the left pixel, there was 28 of them. In 2013, it was only 15. The maximum light intensity in 1992 was 40. And the maximum light intensity in 1913 is 31. The medium and the sum of lights and all of you can see the sum of lights is almost a half. It went down from 1992 to 2013. You can see the stats from 2013 to 29. So you can visually, first of all, being there, knowing the site, being there, I wouldn't say I was there in 1980, but I was there, I traveled past it. You can visually, when you're there, you can see the collapse of the place. Okay, you can physically see these things are just standing empty, and then you can use the satellite technology to also get an understanding of what's happening in that. So the satellites clearly demonstrates, how this place has just become almost to the point of nothing. You can visualize it, and you can measure it through the lights. Now I'm going to show you one more. That's Saldanha Steel. So I've showed you Ezakheni, which is clearly showing where the technology shows you how the thing has just become almost nothing. Now Saldanha Steel, familiar with it?
You've got a mistake there. It's the Cape
Say again?
It's not the West Coast.
Oh, it's the West Coast. It's the West Coast, yeah. Okay, great. Saldanha Steel, anybody know Saldanha Steel? Okay. Okay, so it's a big iron ore plant that was built in just outside the harbor of Saldanha and stuff. So it was built in 1995. Okay, so in 1995 it was built. I think it became operational in 1997 and stuff. That's what this big line, railway line is about. That's just a picture of how the site looks at the moment. So if you go to our satellite technology, you'll go and see there's 1992, there's nothing. You can clearly see there's nothing there from the satellites. The satellite says there's absolutely nothing. I know that to be true because it was only built in 1995 when I was there. Now you can see in 23 how the satellite shows it. You can clearly see the intensity. You can also see the difference in the color, the intensity between Ezakheni and Saldanha Steel. That dark red is basically top 63 and stuff. So you can clearly see how you can look at technology at a specific period of time or in that specific area and use the technology to see whether things are getting bigger, more intense or whatever, or whether it's just going down. So I've used just two examples to try to explain to you or to show you how the satellite technology can be used. Okay, so that is the picture of South Africa in 1992. So that's the annual picture of all these day pictures that's been cleared, taking clouds away, taking all these natural fires away and gas burns and all of these sort of things away. So that's the picture that you download from their website. Well, you don't download just South Africa, you download the whole world. So you download the whole world and then you have to go and get to South Africa. You overlay it with the boundaries of South Africa and you cut it from the what they call a GTIF file. You guys are. So you download it as a GTIF file for the whole world and then you basically go to South Africa and you do. So that is South Africa, the light profile in South Africa in 1992. So just to go one step further, that's the light profile of South Africa in 2013. Okay, you can clearly see the difference. If you overlay it, you can see it clearly. So let's go back again. So I'm just going to switch between the two different profiles. So again, that's 1992, and that's 2013. 1992, 2013. You can see that in Mpumalanga area, just going ballistic and stuff. You can also see if you look at the interior of the country, there's very little there. The coastal areas and the top side of Mpumalanga going ballistic and stuff. Interesting, I did a comparison between Nelspruit and Maputo. I unfortunately don't have it here, but that was also quite a nice interesting exercise to do. Again, I break it down between, so that's now 2013, the last year of the old technology, and this is 2013 using the new technology. So you can also see the difference between the old technology and the new technology. And it becomes very difficult to compare because of the different technologies of taking these specific pictures and stuff. And then that's 2013, the new technology, and 2019, the new technology and stuff. So you download these files, two different websites. I'll show you the websites. You download these files either on a daily basis or on a monthly basis or on a yearly basis. And you get the file that you prefer with clouds, without clouds, etc., and then you start working with those clouds. So that's what they publish, and they publish at a GTIF file. What you then have to do is you have to convert those GTIF files into shape files. Because what that allows you to do is to go and get the numbers. Because at a GTIF file, you can't get the numbers. So it just shows black or white. It doesn't show the difference in the intensity of the white. It just shows white. So to get to the difference in the intensity, whether it's a 0, or whether it's a 1, whether it's a 2, whether it's a 10, whether it's a 15, you actually have to convert it into a shapefile to get the actual data out of this.
I was just wondering if there's a
Yes. So that's why I'm saying it's difficult visually to compare the old technology with the new technology. But if you convert it into a shapefile where you get the numbers, it becomes easier to do. So yes, you're right. In the GTIFF file, it's very difficult. So that just shows you that's now converting the 1992 TIFF file, which is this one, into a shapefile. So now I'm actually drilling down into the arc second, or that square kilometer per se. Okay, where I can actually drill into a specific area and get the intensity of the light and all of these sort of things. So that's how that first picture looked like in 1992, this one here, in a GTIFF file format. And now I've converted it into a shape format, because that allows me to work with the actual data. The GTIFF file, there's nothing you can work with. Okay, so that's how it looked in 92, and that's how it looked in 2013. So if you put these things together, you get basically the same just of it. Okay, but what you can see in the GTIFF file, you can see the difference in the intensity of the light. And that's really what we are looking after and stuff. You can look at Cape Town, you can look at Joburg. It's quite red. So that's 2013. That's now again 2013 with the new technology. And this is 2019 with the new technology. This is just showing you, comparing the two, the TIFF file and the shape file. It's exactly the same thing, just in a different format. So that's Cape Town in 1992. In a GTIFF format, just the black and the white. And on the top right-hand side, it's Cape Town. The same picture just converted into a shapefile, where you're now starting to look at these square kilometers, and you're looking at the data of that specific square kilometers. The more red, the more intense. The less red, the less intense. Okay, so that's Cape Town in 1992. Okay, so what we can do, is you can take that picture. What year is that? It's 2013. So the left one here is that 3 to 63. Remember, 0 obviously means there's no light. It's the middle of the ocean, or it's a desert or mountain, there's nothing. Okay, so Cape Town, so I've got the full array of all the intensities of the light from 3 to 63. Remember I said the old technology has a ceiling of 63. Okay, it's maximum, so that red there in the middle would be 63 and so forth. So what I did then is I went and I said, in this case, give me only those ones where the lights are 2 to 15. Okay, so compare that. You can see this red part there, which is correspond to this part there, is excluded. And then give me the light intensity from 45 to 63, which is basically the middle of Cape Town and 1 or 2 outliers. So the question I want to ask you is, what would you associate? So let's say we got an arc second, a square kilometer, and the intensity of the light in that period is measured at 10 out of, let's say, 63. What would that typically represent? Would it represent a mine? Most probably not. Would it represent a factory? Most probably not. Would it represent a warehouse? Most probably not. Would it represent a house? Yes. Most probably yes. So the idea that we're trying to do now is to categorize this light from its 0 to 63 to say if the light in that specific square kilometer, let's say, is 5, what typically would be there? There is something. There's something there. But what would it typically be? It wouldn't be a mansion with 100 lights, security cameras, and all of these things. It typically would be a little informal little house with 1 or 2 lights. But if there is light intensity, remember it's 1 square kilometer. Okay, so it's not the whole of South Africa. It's just a little square kilometer.
Are the use of LED lights now affecting
It is affecting it, yes. Yeah, so that's some of the downsides, is these electricity saving stuff. And you can see the US. You can see it's happening there, but they're trying to calibrate it now, these technologies, to take those things into account to adjust it. So that's easy. So if there's a 63 light, that square kilometer, the light intensity is 63. What potential is there? It's not a house. It's a guy with thousands of lights. But it is 63. It's most probably a massive manufacturing plant. like Saldanha Steel. If you've ever been at Saldanha Steel, it's got these chimneys that spew out fire like you won't believe, like moss gas and stuff. So now the idea is to say, okay, if the satellite takes a picture of that square kilometer, and we know there's light, we can use the GTIF file to see there's a light. Then you convert it into the shapefile. Now you're trying to measure the light intensity or the sum of lights or the number of lights. And now the idea is to try to put that into a perspective. And now the idea is to use daytime imagery to overlay that number with a daytime picture of that square kilometer. You understand where we're going? Still makes sense? Okay, and I'll show you some stuff. Yeah. Okay, so that just gives you an idea of potentially what we could do. So that's Cape Town. Okay, so let's go to the West Coast. Okay, where we are now. So let's bring it a bit closer to where we are now. So the top left, figure 1, top left is 1992, this area. Okay, so from Stompnius by all the way up. So this is, let me just put it in perspective. So this is Langebaan. So this is Langebaan there, this is Saldanha there, this is Vredenburg there, this is where we are now. I'm too short for this. So this is where we are now in Velddrif, and that's part of Elandsbaai, Stompniusbaai, and that places and stuff. Okay, so this is 1992, and this is 2013. This is old technology. This is 2013, new technology, and this is 2019. New technology. So you can definitely see an expansion of the lights. You can definitely see there's something happening. The place has got bigger and stuff. In fact, you can also, in 1992, I don't have it there, in Dwarskerspos you see nothing, which is 8 kilometers, and in 2013 you pick it up. You also pick up the boats lying on, because at any given time there's about 10 tankers lying off coast here to go into Saldanha Bay to offload the oil and stuff. So they pick up these tankers and stuff. They're using this for illegal fishing and stuff as well now because it's daytime stuff. So they're using this now for illegal fishing and stuff like that. So that's how it looked over that period of time. So if we put it into convert that GTIF into the shape files to get to the actual numbers, you get to top right. It's that same picture, GTIF, converted into the shapefile. You get it in 92, and then you get it in 2013. And you can see the impact of Saldanha Steel. You can see Saldanha Steel there, because remember it wasn't, this was where Saldanha Steel was in 92, that's area there. And you can see how this area just got, and how that sort of created other things. So just Saldanha Steel itself would have been red there, but it created all sorts of other industries. And if you go there, you'll actually see there's a whole lot of other industries that have been built around Saldanha Steel and stuff. You can see also Velddrif, interestingly enough. 92 looks like nothing, very little, and you can look at it in 2013. You see there's a couple of red, which is in light black, which is the factories and stuff that have been set up there. So you can clearly look at this area and say, okay, there's definitely something happening. Okay, sorry, let me just... Okay, so, yes, sorry.
You say Saldanha Steel, but that's not only Saldanha Steel.
Yes. Yeah, that's what I'm saying. The whole area is... Yes, the IDZ. What's at the sand factory there? No, it's the Makosset. I can't. There's a Swedish one that also set up there, which is I can't remember the names now. Yeah, but there's a whole set of industries. Absolutely, the satellite technology shows that, because Saldanha Steel is still at the same square kilometer now that it used to be. Exactly. Exactly. You're 100% right. Okay, so that's the pictures using the new technology. 2013, top right, and then 2019, bottom left. You can clearly see that ceiling of 63 makes a big difference between the old technology and the new. You don't have that bright red of when it was capped at 63. You have it much more diverse. So, interestingly enough, and this is what I want to ask you guys, look at the sum of lights. Now the sum of lights is the number of square kilometers lit times its intensity. Okay, so that's just basically the sum of lights. The number of lit areas, square kilometers that's lit, multiplied by its intensity. So you can clearly see that the sum of lights have gone up quite significantly from 2013 to 2014. You can also see the maximum. Remember that 63 cap is no longer there. It was 67 and went up to 154, almost a doubling of the intensity. So by all means, these things mean there's been quite significant expansion of economic activity. But look at the average. The average actually went down. So what would that potentially mean? Because remember, now it becomes a guessing game. Now it becomes an inference game. Now it becomes, what does these numbers actually mean? Because your sum of lights increase, your intensity increase, but your average decrease. It seems counterintuitive. So what potentially is happening here?
Directed lighting.
Say again?
Lots of directed lighting going down with a cover over it.
Could be. Could be. But remember, the light intensity is increasing. So that accounts for your argument. If you had lots of this energy, then the light intensity or the maximum light would actually decrease. Remember, it's light per square kilometer.
What's about load shedding?
In fact,
What spectrum does it make? What spectrum does it make?
you'll have to go for the technical specs of it. I'll show you the technical
You
specs.
mentioned LEDs, and I think that's
Exactly, there we go. There we go. So there's a lot of increase in low light square kilometers. Yes. So now you could potentially look at this as a per capita thing. So where you can say, okay, if the average is potentially per capita and the sum of lights is potentially your GDP. You understand what I'm saying? So something small have increased much more faster than the something big. And that potentially is GDP divided by population. Potentially. I'm saying potentially, because I can't prove this as a fact, because that's what we are working on now. And this is where we're going now. So to look at if in that, remember we're talking 1 square kilometer. If that square kilometer is a light intensity of 5, what the hell is going on? Or if that 2 slots, that 2 square kilometers next, if the average light intensity decreases in that 2, what's happening? Etc., etc. So now that becomes the inference game. And that's now where it's important that you look at the daytime imagery and overlay it with the nighttime imagery to confirm these sort of things, etc., etc. It could be exactly. Yes. Exactly. Exactly.
apparently the brightest spot on the planet Earth. Do you know where that is? It's in the middle of the Pacific Ocean where there is no land. And it arises because about 5,000 Japanese fishing boats go
Yes.
at times throughout the year. I'm pretty sure, and I'd love to see the pictures, if you had a look around Jan Bay, for example, you would find we're way high on the list because all the chocolate boats are.
Yes. That's why I'm saying, because it's now real time, as soon as they publish, you can download it. They're using this for all of these sort of things. I said, I picked up the boats of flying off Saldanha on this. And I'll show you maybe now. We can go, in fact, we can go there. No. In fact, I've cropped it. Sorry, I've cropped it just to... Yes. Okay, so those are just the numbers for this area. Remember those different maps that I put down? So that just shows you the numbers and stuff. So West Coast, 1992, the average light intensity was 1052. 2013, it's 897. You can look at the medium, the maximum, and all of those sort of things. So the numbers sort of confirm what the various different imagery are showing us to actually happen. So you can actually put these things in a 3D format, as some of those people have done with building those little mountain type things. So you can put it in various different formats, you put it in numbers, you could put it in all sorts of things and stuff, which makes it quite fun to work with. So I'm almost finished. So this is just for South Africa. Okay, so this is the numbers for South Africa. Okay, so this is 1992 to 2019. So I have tried to put these 2 different time series together using that overlap period of 2012 and 2013. So this is the average light intensity for South Africa This is the average light intensity for South Africa from 1992 to 2018. It looks like GDP per capita. It looks not that dissimilar to GDP per capita. Very flat, which we know is sort of what's happened in South Africa over the last number of years. The count of lights, top right, meaning how many square kilometers are lit. Okay, so they measure how many of these things have a number from 1 to whatever and stuff. Bottom left is the sum of lights. Okay. And then right is the lights per capita, just the sum of lights divided by the number of people in South Africa and stuff. So this is the one that most people focus on. So most of the research focuses on this one. Is to say this is your indicator for GDP. This is the closest one you'll get to GDP. In many cases they use this one for determining poverty, income inequality, regional inequality, spatial inequality, whatever you want to call it. So the top left one they use for unemployment, inequality, income per capita. These things, the sum of lights they use for GDP and stuff. That's just, so what we're now busy with is for South Africa to try to see what the relationship between these lights are and GDP. That's just a very simple, who said they love correlations? Somebody yesterday said they are the master of correlation. Wasn't it you, Eva? Somebody said they're the master of correlation. Okay, so that's just the correlation between the log of the sum of lights and the log of GDP. And you can see it's very, okay, this is not causality. Okay, so let me just make it clear. It's not causality. This is purely just correlation. But interesting, you can see the top there, the cap of 63 on top, where it makes it flat, where the correlation seems to be going haywire and stuff. So we still have to correct for it. But it does seem that there's a strong correlation, at least, between those two. So that is sort of where the presentation stops. I just want to quickly show you, if I may, Stuart, and please forgive me, I'm going to, where's my glasses? Somewhere. Oh, add it to the list with the teeth. Oh, yeah, here in front. Okay. So this is Saldanha. Okay, there's the Saldanha Harbor. So this is a daytime imagery in time-lapse format. So that's 85, 86, 87. Now have a look at that space. Something is going to happen there. So that's 87, 89, 90, 91, 92, 93, nothing, 94, something's starting to happen. 95, 96. There we go. What's that? Saldanha Steel. 97, 98, 99, 2000, 2001, 2002, 2003, 4. Look at this as well, Look at all these things. Coming to your point. 06, 07, 08, 9, 10, and so forth, and so forth, and so forth. You can look now all of a sudden, So you can see now, you can take the nighttime imagery, and you can look at the pictures and the lights and the intensity, and you can overlay it with the daytime imagery, and you can get a complete picture. And you can actually measure, starting to measure things. You don't have to just hypothetically talk about these sort of things and stuff. The data. So the first sets of data is a NOAA. That's where the first sets of data are all located. That's the old technology from 1992 to 2013. So that's where the old sets of data are located. That is just the name of the different satellites. And as I said, you download the GTIF file that looks something like this. And then obviously you have to go and cut out for South Africa. So that's the old sets of data. The latest set of data is on that website. We are located in tile 5, and there they are. So 2019, monthly. So those are all the monthly data and stuff that you get from it. So you just go and then you download the specific data. Then you go into just a normal GIS program. This is just QGIS. So that's that picture in 1992. And if I take 92 off and I go to 2013, something is supposed to happen. There we go. That's 2013 and stuff. So now you can just go into a normal, I don't know why it's doing this now. You can go into a normal GIS program, and you can go and put all the data in your, I don't know why it's doing that now, but anyway, you can go and do it in GIS now and go and do all your playing and stuff in GIS and stuff. Okay, so that's basically where we are at this moment. So what we're working now is to do each municipality. So to do all the stuff per municipality, build a database per municipality, and then we can start looking at the different regions in South Africa, how they compare and stuff. Just interestingly, what's the GDP percentages for Joburg to South Africa? What's it, 20%? No. KZN is about 16% GDP.
Western Cape is 14.
Yes, Western Cape is 14. Gauteng is, what's it? I can't remember. Yeah. Now we've done those numbers, and that basically correlates. So the lights as a percentage of total lights for KZN is 15.9%, where the GDP is 16%. So already some of these numbers seems to be stacking up. So those are what we're doing now, is to intuitively look at these numbers to see just basically where they correlate and all of these sort of things and stuff. But yeah. So that's where we are at the moment. Anyway, I'm going to leave it for there for now.
You said the first set of data was available at the NOAA?
Okay, so the first sets of data are
Where's the second set?
available, this one here. It's that website there, Earth Observations Group. So those are where your two sets of data is. As I said, you download the data in a GTIFF format for the whole world, and you have to go and get to the part that you want, whether it's South Africa or Lesotho or whoever and stuff, and then you get that TIFF out, and you can cut it in the GIS program, and then you convert that TIFF file into a shape file, and then you have got access to all the data and stuff. But it's big because you're talking millions of these things. So it's big data files.
We've got a very sharp
I know.
focus at 10 to 11.
Yeah, that's,
Let's give Francis
yeah, yes, yeah.
Sorry, Clive, I didn't get the URL again. Can you tell us again?
Say again?
What's the URL at the top? What is the name of the site?
Okay, so this is the Earth Observations Group.
Sorry?
Earth Observations Group. But I'll show you all the stuff. We can do it in tea time. We've got are you up now, Francis? Okay. So I'm going to hand